professor Brasseur. Ele foi meu diretor no NCAR, muitos anos atrás. E, desde então, ele vem sempre aqui nos dar a honra, né? Nossa, eu não estou enxergando nada, porque estou sem óculos. Então, agora ele é pesquisador no Max Planck, sempre foi, né? Desde aquela época, Max Planck, e também do NCAR. E ele veio para um evento da FAPESP e vai nos dar a honra de fazer a palestra. Tá certo? Por favor.
I'm going to remove my mask. So, good morning to all of you. I'm really happy to be here. I've been here very often, including in this building and in this room here. It's always good to find friends, Fatima, Perola, I see Paulo and many others. I see that some are online. I see Rita online. I see Pablo online. Many others probably online. So hello to everybody. So what I would like to do today is to do basically a talk that if I had been a meteorologist, I would have done this talk in 1920. The need to create a network of meteorology for the weather forecast. That was the topic of the 1920s. And so now I would like to do the same thing, but about air quality. The need to go and think about a real good worldwide system for forecasting, but also observing first, and then forecasting air quality, and finally attributing the sources of air pollution. So let me start with an introduction and just pick a few pictures that were probably propaganda a bit in the 1940s or in the 1960s when the Industrial Revolution was a sign of economic development, and people were showing how the factories were effective, how China lead therefore to deterioration of water quality. It creates climate forcing. That's true for methane, that's true for ozone, and it has direct and indirect economic impact, all these problems. And here some people have been evaluating this. You see here in the OECD country, and in addition China and India, you see that the economic cost resulting from only outdoor air pollution was about 3.5 trillion. And if you look at the 53 member state of the European region of the World Health Organization, you see also how many premature deaths you have, and the cost is estimated probably to a high level. People are talking at least more than 1% of the GDP. Now, a lot of people die prematurely from air pollution in the world. And the New York Times had a paper on July 8, 22, not long ago. It was an essay by David Wallace Wells, who has been working books on climate change. He's a climate person, but he starts realizing that we have forgotten to include air pollution in our thought. And he said air pollution kills 10 million people a year. Why do we accept that as normal? So that's a kind of an interesting question for social scientists in particular, psychologists. You know, if we have 3 people dying in a car accident, it's in the news. If we have 10 million people dying from air quality, it's normal. We don't even talk about it. So how can we address the problem? Well, we can take short-term action, we can take long-term action. Short-term action is really to try to avoid air pollution, acute air pollution episodes, and we can do that by forecasting them. And then if we have a bad forecast, we can take action and say, do not drive, do not produce this kind of things in industry, etc. But we can also look at long-term action, and that's really to reduce emission in the long term, and to do that we need to attribute essentially where the sources are. So let's take a little bit of an historical perspective. This is now just for our fun to see how things have been evolving. So if we take tropospheric ozone, we could take aerosol also, but I'm going to focus here on tropospheric ozone. In the 1950s, a Dutch biochemist, so biochemists have been doing a lot for atmospheric chemistry, R.E. Hagen-Smith, who was at Caltech in Los Angeles, in Pasadena, he kind of found out that the smog that people had in Los Angeles was the action of hydrocarbons, reactive hydrocarbon, and nitrogen oxide, and they were released by either cars or oil refineries and so on. But perhaps what was really an important input to the discussion came 20 years later, because Hagen-Smith had this feeling that, yes, something is happening between hydrocarbon and NOx, but nobody understood that there was one compound that everybody in the world should know, and that's OH, the hydroxyl radical OH, which you see here, which is really, according to Chip Levy, who is here, is produced essentially by the action of basically ozone and water vapor. Ozone is transformed, photolyzed, produce O single D, and it produces OH. So you probably all know that, but that was the basis for the development of atmospheric chemistry, because they found that OH reacts with essentially everything, in particular carbon monoxide and methane, and so initiate a chain of reaction that is always regenerating OH and also NO and producing ozone in the regions. And so in reality, this is the scheme that Levy showed in 1970. It was not comprehensive, but historically it's very important to see this, because he put OH, HO2, and he showed the cycle happening with NOx there, and ozone is kind of leading to the formation of OH. And so this scheme here is reproducing ozone. He didn't really mention that too much, but in fact, to produce ozone in the troposphere, you need to have ozone coming from the stratosphere to initiate the process. Now, there has been then a number of theoretical studies involving Paul Crutzen and Bill Chamides, and they really indicated that ozone produced, and when I say ozone, I should say today secondary species, and that includes also not only gas phase, but also aerosols, particles, are really the result of those complex mechanisms. And so this was the basis here of Hagen-Smith. This is what essentially Levy showed, more complicated, not as simple. And in fact, you have different situations. If you are under a low NOx or a high NOx situation, the scheme that function, the one that are in red, are different depending on in which environment you are. And that makes, of course, the issue complicated in terms of mitigation, the formation of ozone, because the action you have to take depends very much on how much NOx you have. Now, what has happened since? In the US, there has been recently, maybe 3-4 years ago now, an academy report, and the conclusion was that our understanding of atmospheric chemistry, I would say since 1950, since 1970, when Levy showed this scheme, has advanced sufficiently that it is now clear that the field is central to addressing vitally important societal issue. So suddenly, atmospheric chemistry is not a curiosity problem, but it's a societal problem. And addressing this issue depends, of course, on a deep understanding of everything, but it also depends on predictive capabilities that we should have on the local, regional, and global scale. Now, that's in the US. In Europe, people established a project called the Copernicus European Project. It is a flagship program of the European Union to monitor the Earth and its environment, and also to prepare for crisis, security risk, natural and man-made disasters. Something that is important, something that you should have also in Brazil, but it seems a bit difficult at the moment. So let's go and talk a little bit about what these projects and programs are doing. Let's talk about the short-term aspect with observation, analysis, and forecast of air pollution. So if you want to do a prediction of air pollution for the next 3-4 days, you need a system that involves different things. First of all, you need to know how the weather will change. You need a meteorological forecast. Then you need to have some input. You need to know the emissions of chemicals. You need also to have maybe observation that you will assimilate in your system, for example, space observations. And then you need also in situ measurements. So the networks that exist on the ground are very important because the satellite do not see very well what happens in the ground. And all that can be assimilated or used for the evaluation of the air quality prediction. Then, of course, you have to do the prediction, and you have to provide product, you have to disseminate them, and then you have to validate them to compare them with observations. So that's how a forecast system is done. And of course, the 4 elements of a forecast can be summarized here. You need air quality monitoring. So you need in situ observation using different kind of analytical method. You need to use remote sensing observation. You need to know the emissions, and you have to get the models that allows you to do the prediction and calculate what you think will happen in the next days. So let's go a bit through those elements. Let's start with the global and regional scale gas and aerosol trend in the emissions. Let's say a word about the emissions. So we have to do that emission inventories. And we have now today an effort that exists to provide global scale emission inventories. You see here an example. This is for carbon monoxide, CO. It's on a particular date. It doesn't really matter. You see the value here in kilo per square meter per second. And you see the world. And you see essentially that there are regions where the carbon monoxide emissions are high. This is essentially human activities. You will probably also look at fires that occur in the savanna and in the forest. You will see, for example, these are the ships. So they take into account the ships, and you see some emissions, and sometimes you see corridors of ships. You know, ships go here along the coast, go to Europe, for example. But these are emission inventory at about 10 kilometer resolution today. So one of the questions, of course, is that how good are those emissions? We don't know. I mean, this is a big effort involving a lot of people taking best judgment on using all the data they can find. But for example, I think there is still an effort that needs to be made here for South America where more input needs to come. We have this, but how good is that? Who knows? So just to show you the uncertainties, I took China because we all talk much about China. So what do we know about the emission of CO in China? And this is now the evolution between 1980 and 2020. And you see that we have different inventories and we have different values. So what is interesting is to see that some of them are decreasing here, showing that China is improving in terms of the emission, but some others are not. So if you want to look at trends, for example, in China, you can see very different situation. This is now just for a few years. You see the trend. These are the Chinese inventory, essentially. These are more the European inventories. So there are a lot of disagreement in the emissions. So we need to work further on that. By the way, those emissions are at 10 kilometer resolution. Some models, when you go to urban scale, have much better resolution than 10 kilometers. So you need to find a way by which you get emission inventory at maybe 1 kilometer resolution or 100-meter resolution, whatever. And so this is what a typical 10-kilometer resolution gives you. This is CO emissions for transportation. Well, it's very vague. This is around Beijing. And so if you take now the traffic that you know around Beijing, see the center of the city is here, you see all the rings around it, you can use this information as a proxy to upscale or downscale this, I should say, downscale this, and then this is the amount of the CO emission you are getting. So this is done by one of my students from China. You see it here for residential. This is what the emission inventory gives, and here you see how she's been able to downscale that. Same thing for agriculture over there. Okay, so far for the emissions. Then we need to go to remote sensing observations. Now we have much more data, much more knowledge from the space, but it's mostly the vertical column that you have, like here, NO2 vertical column, and again you see the regions, but you have very little information at the surface unless you treat your data in a certain way. Now, there will be more satellites going on. I don't want to go into the detail. These are the European, the Copernicus Sentinel series that is going to be there. And by the way, this is how these data are basically introduced, assimilated in the forecast of air pollution by ECMWF. You see that the number of data, the number of satellites available is increasing, and people are making use of that. The next big satellite system that will be available are geostationary satellites. So these are satellites that will be over the equator. You see here 1, 2, and 3. There might be another one here. And so essentially they stay there and they look all the time at a region to basically see what happens hour after hour. And there is one that's already in orbit. It's GEMS. So they give you all the information. So this is now flying. The next one should go in December. That's the American one. And then the last one here is the European one. And so they will have very high resolution, and they will monitor air quality and therefore, in a way, emissions on a very, essentially on an hourly basis. I think there are other projects now to do more of that. But again, look, everything is in the Northern Hemisphere. We clearly need satellite also in the regions of the Southern Hemisphere. And so hopefully that will come. I know that some people are very interested now by Africa because we know very little about Africa. And so having a satellite over Africa will help. I think it should be one over South America also one day. Okay, let's go to the models quickly. And here, when we talk about the model, we have to talk about which scale we are talking about. We can start with global scale. We can go to continental, regional, local scale, and even urban scale. And basically, most of the model really don't go much further than the local scale. But there are attempts now to go to basically going from the mesoscale models to the urban scale and even to the street level and try to see what happens. So I'm going to show you a few examples of that in a minute. Let's start with the global scale. And here, again, Copernicus in Europe, as I mentioned earlier, is trying to do a prediction of air quality, but basically not only air quality, looking at the ozone layer, looking at the climate forcing, looking at how radiation penetrates to the surface. That's important for solar aspect, and trying to derive the emissions at the surface. So it's a real integrated system. It uses, they say, 280 million observations every 12 hours, data from 7 satellite instruments, and provide 14,000 maps of different things. I don't know where they are, but that's what they claim. And I'm going to pass this one, but I'm going to show you the forecast for today. So we are, I think, the 11th of August. This is carbon monoxide. And you see what the forecast is. So you see, of course, high value. There must be a lot of fires here. the fires in the US, I think, I mean, they take into account the fires, for example, important for carbon monoxide. You see here probably pretty high level. And then you see also the cities that are emitting. So we're going to zoom a little bit over South America. Okay, this is South America. So you can see Sao Paulo here, Rio here. You see high pollution along the Andes in Chile. And you see probably some fires happening in, you're burning the Amazon too often. And then you see also transport. I think this is coming from Africa and really touching the northeast of Brazil. So we can do more zoom, and you see it more. But it's still with 40-kilometer resolution, so it's not really detailed. So we need to downscale. We need to go to higher resolution to get more information. And so what Copernicus is doing, they have 9 regional models that are driven by the global information that I just showed you. So the boundary conditions of these regional models are driven by the global model. And then those different models calculate, in this case, over Europe, see here, basically the air quality at a resolution of just a few kilometers. And here are the results for certain species. You see ozone, NO2, CO, what is it, PM10, PM2.5, and SO2 by those different models. But then they calculate also the mean value from the different models and the median value. And essentially, I'm looking here, this is the median here. This is, you see the error here that shows you the error compared to the observation. And so the conclusion is that the median value of those 9 models is often better than any of the models. And so it's a multi-model prediction. You need 9 models in this case to get some sufficient. You have to assume that all these models are independent, of course. And if you do that, you see that the mean value is a bit better. This is the root means square error. Now, we did the same thing for China. I've been talking about China. Here are the different models, the different groups. So you see European groups in blue, Chinese groups in red. And so we have been calculating exactly the same thing. So we have forecasts by model number 1, model number 2, model number 8 or 9. We do pre-processing, and we send everything in a central database that is at the Dutch Met Service. They take all that, they calculate the ensemble, they calculate the medium, and then they put it on the web. And then, of course, what is also interesting, we get the data from the station to verify the prediction, and the data is also here. So you will see example of that. I'm going to pass this one. So this is an example of NO2 and ozone in Guangzhou. This was calculated in June 2017, so it's a bit old. You see that the median is in black for ozone. This is on from midnight to midnight. And you see the observation. You see, of course, there is a gray zone here, which is essentially the dispersion of the models. You have a red zone, which is the dispersion of the model of the observations in the region of Guangzhou, because there are a lot of stations there. And then you compare, and you see that in this case it's relatively okay. Oops. There's another example here, and I think this is in Beijing. Yeah. So you have PM2.5, you have NO2, you have ozone. These are now 3 days. And you see in red the data, so the reality, and in black is the prediction. And so you can see sometimes, like here, you have a big decrease in PM2.5, also in NO2, big increase in ozone. So what's happening at that time? There was ice, fog, and so on. So the weather changed very much, and it highlight the importance of having a good weather prediction to do a good air quality prediction. Now let's go to another place which you probably know a little better, which is called Sao Paulo. And this is a prediction for 20 July 22 with different malls, I think. Well, no, in this case, it's only the WAF mall with, you know, different conditions. But now we are working, I'm showing you this because we're working part of the Climapolis project into an intercomparison of different malls. And there is a paper in preparation with groups in Brazil and groups in Germany to do a system for air quality forecast, essentially in South America, and in particular in Sao Paulo. I think, whoops, what's this? Can I get rid of this? Yeah. And to do something in South America. So let's go a step further with really local downscaling. So we want to see what happened at the street level. I think this is Paris. I don't know exactly. Looks like maybe it's not Paris. But if you go on the street here, you have pollution that is not necessarily completely uniform. By the way, Google is very interested in providing this kind of prediction. But they need inventory at a very, very result scale. So they have a project in 2 or 3 cities. One of them is Copenhagen. And so what they do now, they look at the emissions on the street, for example. They know, is there a restaurant? So if there is a restaurant, there must be some emission from the restaurant. So they go to that level of detail. Are there cars passing? Is there a garage? Are they, you know, probably a gas station and all that? They take all that into account and they try to do that. Now, we don't do that so well, but of course, once you go to small scales, you start to have a much more difficult problem because your boundary is very, very complicated. You have, of course, the external to the city boundary, then you get into the urban boundary. You have a different mixing layer, you have different emissions, you have different exchanges, and you have now eddies and you have turbulence that is playing a big role inside your building. So we're trying to go in that direction a little bit. And here we picked the city of Hong Kong. Why Hong Kong? Because look at the streets. You have Street Canyon, very interesting. You know, buildings are very high, and then you have a lot of emissions inside because of the car. And then you have mountains, you have water, you have buildings, it's crazy the way the system works there. So essentially what we're trying to do is to use what is called a large eddy simulation. So we simulate essentially the eddies, the turbulence that is occurring inside the urban area. We have, of course, emissions that are pretty detailed, take into account here the traffic, for example. And you can see here basically the prediction on different scale. This is about 1 kilometer scale. This is from the regional mall, so 900 meters. This is 100 meters, this is 33 meters resolution. And now you start to see the pollution here. This is NO, this is NO2, and this is ozone at a relatively detailed scale. And if you compare this with this, you can see that there are differences because the production of ozone is affected by nonlinear processes, and so it is resolution dependent. This is now the vertical cross-section. So this is the 900 meters. So you see NO going up here, NO2. This is ozone. Ozone is somewhat reduced, titrated by NOx. But if you work at 33 meters, you see that it looks very, very different. So it's kind of interesting to look into that. We compare with observation. This is the 900 meter resolution. This is the higher resolution, and you see the data which are in black. So we try to improve a little bit the prediction in that way. Now there are ideas now of including the building effect, which we did not do yet. And so these are some attempts to to really look what happens in between the buildings and how turbulence affects things. So it's expensive to run on the computer. But of course, as we have global, regional model, we can also ask ourselves, can we not combine all that? Why do we need global model on one hand, regional model on the other hand? So now we're working on models that have essentially the capability of giving you a global picture, but zooming in a region where you would like to have basically higher information. And so this is done at NCAR, but it's a community initiative, and everybody who wants to participate is welcome to participate in this project. And so you see here, for example, one grid that is used. So we have maybe 100 kilometer here resolution, and then we go down to 14 kilometer in the region of interest. That's another grid here. That is the coming from MPAS. This is more like what's called a spectral element system. This is a grid that is hexagonal, and you see over the US here the hexagon are much smaller than here. So it is a model that is global, but it gives you regional information, and the cost of adding the global aspect to the regional model is about 10 or to 20%. So it's not a lot of increasing cost, and you can now have impact from far away on your region, which you don't have in your regional model. So we are applying that, for example, in South America. So this is the grid. So it's a spectral element version. And you can see here we have a grid that is zooming over the whole continent of South America. And here's a zoom on that. You can see that we get a pretty high resolution. And we want to build a prediction system for air quality based on that. And I have an Argentinian student from Buenos Aires who is in Hamburg, and he's applying the model to South America. And so I'm sure that you will be interested in this and maybe get involved. That would be really great. Now, let me finish by talking and saying that our community, which has been doing a lot of research, needs now to think a bit more about society and about how to make sure that these products can be used. So there is a need to essentially cross what we call the valley of death, that some people call the valley of death. We are doing a lot of research, but there is also the need to move into a more operating phase. And so to do that, we have to cross this valley between the two by bringing the products and services to a high level of technology, and then to deploy that by having essentially exploiter who can use those products and distribute them or put them on the market. So we have a project called AQ Watch. There is a consortium with people from different countries, mostly in Europe, but we have people who are using those products in 3 places, because the purpose of the EU is essentially to export outside Europe these products. So University of Chile is involved, we have 2 groups in China, and we have NCAR that is involved. And so the kind of things we are doing here are to develop essentially, let me see if I go here immediately. We are developing essentially 5 modules. One is a global and regional air quality atlas. I mean, we have a lot of atlases, geographic atlas. We now have climate atlas. What about having an air quality atlas that is based on all the information we had in the past? And so anybody can see how air pollution and all the chemical compounds, all the emissions, everything has been evolving as a function of time. That could be very useful for people, you know, even the mayor of a country wants to know how is my air quality changing, what has happened in the past. It can be useful for schools, etc. We have a second module that is an air quality attribution and mitigation. I'll show you that a little bit later. We have a system of forecasting dust, but also another system forecasting what happens if there are fires in the region and how visibility is affected, so that people could, if a fire is initiated, you can see a bit what's going to happen for the population in the region. We have an analysis system for fracking. In some country, they want to start fracking and get gas out of the ground, and that has a lot of impact on air quality. And then we have the more traditional air quality forecast in urban area. And so what we're doing is to do that with stakeholders. So we have a spiral loops. We start the loop here. We have our initial views on the concept of these products. We dialogue with prime users. They are in Chile, they are in China, they are in the US, about what they think about those products, how we should modify them or involve them. We move them in the development of the product or services. We go back and ask the prime users to evaluate them. They suggest modification. We start a second loop, and then we go to a third loop. And when the third loop is over, we go to commercialization of this product. And of course, that requires a development of a business model. And hopefully, we give them companies, for example, 3 years to put it on the market. So we're working with companies to do that. So here's an example. This is the atlas. So the atlas, well, we have the global atlas with all countries of the world. In addition to the states, we have a regional atlas where we can produce information at a higher scale, both spatial and temporal. And then there is added value for public authorities, which are listed here. And we try to put that on the market in a way. And so you can see here, for example, we're working with a number of small companies who are interested in air quality and represent different aspects of the market. And the discussion is not necessarily easy because they have their own agenda, they need time to decide, but essentially we're trying to identify potential exploiter for those products. So it's a different way of operating now. It's really to work with people and to work with the market. And so we will see if we succeed. We have another 2 years to go and to finish this project and see if those 5 modules can be really used in reality. Finally, we talked essentially about the short-term issue, which is prediction. But what about the long-term challenge, and in particular attribution? So the question is, can we kind of modify a little bit our emissions in the model and see what it does on the pollution levels? And if that's the case, can we mitigate and reduce these emissions? So, for example, here we take the region of Santiago in Chile, and we have essentially this is PM10. And so you can see the PM10 as predicted is varying with time, but you can see where the PM10 is coming from. So you have different sources with different colors. And so I cannot read them very well, but you can see industry, you can see transport, you can see agriculture, you can see natural sources. And so by having this, you can hope to basically know what, on that day the source was mostly this one. On this day it was mostly this one. So you have an idea of how you can adjust your sources and modify them. This is another example now in the US. This is about CO again. And you can see the percentage contribution of CO. So if you are, for example, here in Colorado, this is blue, so it's only 1%. It's due to, what is this? Should go here. So if I'm here, it's green, so it's 7%. It's due to anthropogenic activity. But it's red here, it's 40, 50%, 60% from outside the state. So you know exactly where your CO is coming. And you know that if you want to take really action, You cannot do it just locally. You have to deal with the transport from other regions. So you can do that for all the species. This is just an example. And then, of course, we have the mitigation. So this is a screen that we're offering. And so here we are in Santiago. And you see, this is, what is it? PM2.5, particles. So they have quite a bit of particles. You see how much here. But then I have some switch here. I'm going to play with my emissions, really to play. So I'm going to leave the agriculture at 100%, at what they are. But I'm now going to reduce my road traffic by 25%. Why? Because this is maybe achievable. So if I reduce my cars traffic by 25%, I reduce the residential combustion in this case, so then I get a different situation. And so I can give this to policymakers. They can play on their small computers, on their laptop. They can see, what if I do this? What if I do that? What will be the consequence on air pollution? I think I'm getting close to the end. Oh yeah, I have a few future challenge. Well, maybe we can finish with that. What are the future challenges? First of all, support research. That's remain very important to address unresolved scientific questions, including organic chemistry, very important, still a lot of unknown there, aerosol physics, and composition, and also heterogeneous processes. I mean, these are issues that are still very poorly known. Develop a consistent international monitoring system for air quality with a particular effort in low-income countries with coherent quality standards. Improve the accessibility of satellite data. We have a lot of satellite data. We don't use them because it's too difficult. Develop added value product to make use of these data. Accelerate the execution of chemical modeling system by using artificial intelligence. You know, those models are very expensive to run. You need big computers, so you cannot really operate them. I'll show you an example in a second. And then include atmospheric chemistry knowledge into an Earth system approach. So you cannot just say pollution, pollution. You have to put that as part of all the processes that are in the Earth system. So artificial intelligence, you know, people are starting now to use neural networks to analyze and forecast air quality, and they take low-cost sensor data to include that. So I'll give you an example. This is now a prediction done by a private company called Plume Labs. I forgot what it is. I think it's the air quality index, because they don't go into detail. They just say, where is the good air quality? And so here, for example, there must be a lot of particles from the desert. You see other places where the air quality is not great, but this is using input from a low-cost sensor. And then, you know what they can do? They can zoom in one country. They can zoom further, in this case, near Los Angeles. I gave a talk at JPL, so I took that. And then you can see they even give you value at the street level. Now, how good this value is a big question. You know, you can do anything, but, you know, those companies do not care too much. They care about selling their products. They don't care so much about the quality of their products. So it's good that there is an academic community to be looking to that. And then finally, putting everything in an Earth system feedbacks. And this is taken again from this Academy report in the US that I showed you, by showing that essentially, you know, when you do atmospheric chemistry research with oxidants, dynamics, particles, cloud, biogeochemical cycle, you need to link that with the forcing that are coming from human activities. You have to look at the impacts and the societal choices that are made, and all that needs to feed back into the system. So I think that the holistic view is really more and more important, and this is basically my conclusion for today. I think there is still a lot of work to be done, but you can realize that atmospheric chemistry, even though research is still very important, has entered in a relatively operational world today, because the science has made progress so fast since 1970, when Hiram Levy had this first loop that he proposed. We have learned a lot, but there are still, as I said earlier, big issues, big questions, and there is a big role for the atmospheric community, for the academic community. And so, good luck for the future. Thank you. Maybe I'll leave my last slide.
Thank you. Thank you very much. It was very comprehensive, enlightening presentation. I'd like to ask if someone wants to make a question. Or maybe people
maybe
that... Yes, I don't know if... Rita that's there, I don't know if she wants to talk. And Fabio? Okay.
Pablo is there, yeah.
Hi, thank you very much for your talk, Guy. It was really very nice. And what I would like to ask you is that we have our understanding has really enlarged, but for something, if we go to a simple example, like we know that we shouldn't eat as much French fries as we would like, but anyway, we do. And so the similar thing applies to air pollution. We know that what the sources are, but still we are still emitting them. So what would you suggest for this scenario?
Yeah, it's too bad you didn't hear my talk. I gave a talk yesterday at a meeting from FAPESP. It was more on climate. It was not on chemistry. But at the end of my presentation, I was thinking also, just like for chemistry, what should we do about climate? And should we mitigate or should we adapt? And we can say that, the same thing for air pollution. And so what I was saying was a bit controversial on purpose. I said, of course, we have to mitigate as much as we can. We have to take all actions that we can to reduce the emissions. But how will we do it? Will we be reasonable enough to take action? And in the case of climate, you have to reduce the CO2 emission drastically in just a few years. And I don't think society is really ready to do that. Just for like the French fries, people still eating French fries. So in fact, our society has not been trained or has never really taken action to reduce a danger coming. But it has adapted. So we have in our vein, we have always adapted to every big changes that occur in our system, which was much easier than for the society, than to prevent something to happen. So it's clear that in the case of climate, we will probably not reach the 2-degree limit that the Paris Agreement has been suggesting. I mean, we should do everything we can to do that, but we have to be prepared for the case we do not get there, and we go to 3 or 4 or 5 degrees. And so clearly, we have all the science that tells us what's going to happen. All the models predict climate change. All the models are there to say how severe it will be. But nobody really is looking at what would happen in that case, because the whole research is focused on this assumption that we will reach the Paris Agreement. Well, in atmospheric chemistry, it's a bit the same thing. Everybody knows that so many people die. Nobody cares. I showed you the article in the New York Times. So the only thing is probably that it will be adaptation. Now, what is the easiest adaptation we can do? Easiest adaptation is to do nothing. We do nothing. Zero solution is the best, easier, not the best, the easier adaptation. But can we really move into this idea of attribution, looking at what is polluting, what should be done, and essentially highlighting not so much the amount of pollution that we have in the air, but highlighting what the emissions are here, 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 and here, and taking action against them. That's probably the best way we can address the problem, I think.
Okay, questions?
Thank you.
Yeah, nice talk. You mentioned the use of the new kind of regional between quotes models, with different grids and so on. Do you think that in 5-10 years, all regional models will be global? What's your view on that?
Well, I don't know. I cannot predict that. But what we are trying to do by creating this new multi-scale model is really to replace WRF-Chem. WRF-Chem has been there for a long time. It has been changed by a lot of people, so it's becoming very complicated to use. So we want to go back to a clean situation. And rather than building a new regional model that becomes a community model, we're trying to build this mixed multi-scale model, and we would like it to become basically a community model. And I always say as a joke almost, but it's not so much a joke, to the programmer, I say, this model needs to be so easy to use, because these models are sometimes complicated to use, so easy to use that it can be implemented, for example, at the Meteorological Service of Egypt. They should be able, they don't have probably the programmers and everything, they should be able to get it with good documentation, put it on their relatively small computer and run it. Otherwise it will be a failure because nobody will use it. So we will see. But it will take another 5-10 years before it's really, really operational.
And thank you for the marvelous presentation. And I have a doubt about the variation about the models in global scale, because the forecast of air quality of atmospheric pollution is very sensitive to this huge variation that we have when you are working in smaller scales. So there is any discussion about things like the concept that Ted Shepard bring it to the climate models of star lines, for example, or things like that that are more physically consistent than taking a statistical median or average between the models?
Yeah, I don't know. I mean, you're talking about Ted Shepard's thing. I don't know exactly what he has proposed. So.
It's basically the proposal is that the model assembly is not a physical consistent system that we can use because
it's not consistent.
It's not physically consistent.
No, that's true. There is a lot of inconsistency between models and also inside some of the models. But, it's perhaps the best we can do at the moment. The model has always a bit of a, kind of experimental. You have to see if it works. All models are wrong, but models are very often useful. So, and of course, these kind of claims that Shepard is doing are interesting to make progress. And progress is happening, and people are listening to that. But we cannot wait until we get the perfect model. We have to work with what we have, and we give decent results, not perfect, but decent.
Okay, thank you.
Hello, Professor Brasseur. Thank you for such an outstanding presentation. I have a couple of questions. First one is also related to the models. When we look at the modeling in Beijing that you presented for ozone, PM 2.5 and stuff, I noticed that the uncertainty bars are quite large, the shaded areas in the graphs. I was curious about what are the major challenges for reducing such barriers, what inputs are responsible for such large uncertainties, which is comprehensible because you're using a quite large number of models. And if I can ask another question, would be about the importance of the N2O for the forecasting that you're doing, because I haven't seen much in the presentation about that.
N2O.
N2O, yeah.
Okay, first issue. In order to do a statistical analysis of using different models, you want the models to be independent. Because if you have two same model, it's not going to give you any information about the uncertainty. So when we decided to do this, you know, the first idea was, oh, maybe we need to compare them all and see what the discrepancies are and try to address them. And so we see, you know, they're using different emissions. Maybe we should decide on which emission we're going to use. So we refuse to do that. Because why should we take this emission and not this one? I mean, everybody has been doing the best possible effort to get a good emission. So it's part of the uncertainty. So we said, okay, we're not going to transform our model. We're going to take them the way they are, and we're going to compare them. That's one of the reasons we have such a different, some differences between the models. They have different resolution, they have different emission, they have different dynamics, they have probably different rate constant in the chemistry, etc. And so unless we identify an error, you know, if somebody say, oh, I made a minus sign and I should have put a plus sign, and it's an error, so we correct the error. But otherwise, we let it go and see what happens. Now, it also, when you do those forecasts, it's very important and interesting because you can see the diseases of models. Some models always produce too much ozone, always, or most of the time. So there must be something in their model that is not the way it should. Other models have other diseases. Some models show a nice peak at the rush hour, some others ignore it. So then people learn from these kind of things and they can improve their models. Now, just for a little story, I found out, you know, the median was better than individual model, except for one model. A Chinese model was always better than anybody else. So I started to ask myself, how do they do it? You know, those Chinese, they always have tricks for everything, but they won't reveal. So this was a Nanjing University or something. So I wrote him an email and I said, could you tell me why your model is always better than everybody else? What do you do to do that? I mean, sometimes I'm thinking that you're taking the observation and call it model or something. So good. And he said, no. And he explained me in great detail what he's doing. So what he was doing is this. He runs his model for 1 week. And then he compares with the observations, and he says, oh, my NOx is a factor of 2 too high. So next week, I'm going to take my emission, but I'm going to divide them by 2. Much better. But he still has 10% discrepancy. So the following week, he reduced by 10% again. And he does that every week. He looks at how well he has performed the week before, and he makes a correction in his emissions. And of course, I tell him, yeah, you're violating probably some law. Well, we're doing forecasts, so we don't care very much about the science. We just want to be close to the observations, so we tune our model to do that. And in fact, when we did South America, I showed you Adrien de Roubaix in my group was doing those predictions for South America. We now did the same thing, and we improved the prediction very, very tremendously. So you can play a little bit when you do a forecast, and in fact, the weather people do that too. You know, they always miss something, they tune their model, and then they improve the forecast. And sometimes it's not based on any real scientific rationale, it's just experience.
Okay, questions? Okay, I have a question. We are always very worried about the spatial resolution. But one problem that we have with when we have these mobile emissions is the temporal variation. And that is not easy because you see today the traffic is terrible, but tomorrow it cannot be so terrible. how we are always worried about the spatial, but not the temporal. Do you think we could use artificial intelligence to have this described, like considering the sampling of many weeks and then including this in the model?
Yeah, perhaps, but in fact, the people who do artificial intelligence do that. What I think probably would be needed is to have information of the traffic live, and Google does that, I heard. And so you can connect with Google, and they will probably give you the traffic at this time.
No, they will sell. No, they cannot. They don't.
They
are
sell
not.
it. Okay.
Yes,
They
they are
sell
not
it, yeah.
giving us
Okay.
free. We
All
are
right.
asked already.
Okay, okay. But maybe we can do one day a project with them, and then they will maybe sell it half price. Yeah, maybe. I don't know. Yeah. No, but that's they do that for the ships now, because for the ships, every ship has a GPS, so you know where they are. At least the big ships. See, there's always a problem. So because you do it with the big ships, then you know where they are, and you don't do it with the small ships. Now, if you go to China, for example, you have all these barges on the rivers. These are small ships. They emit probably a lot of stuff. I mean, when you see the engine, probably more than the big ships. But you don't know where they are. You don't know what they do. So, emission is a really tricky issue.
Another quick question. What do you think about the use of low-cost sensors in countries like here in South America as an alternative to regulatory systems?
Okay, low-cost sensors are not always very accurate, right? But if you use many of them, and if you treat them appropriately, you can get some information out of them. So it seems to me that probably what we need is like in South America or Africa, where you don't have a lot of stations, is a combination between satellite data and low sensor and probably a few good stations. That's probably the first step. The better step would be to have many good stations.
Thank you very much for your awesome presentation. And I have like a comment questions. I was very happy to see that you talk about the social part of the equality problem. But I think that in the social part, there is also the political part of the problem, right? Because I think that we have the science right, but we talk to our government or we only talk this in this detail in these events, right? And for the government, they don't care and they don't do a lot, right? I come from a country in South America called Peru, and we got an environmental ministry, but we have an air quality network. We got data, but it's not so, it's public, but we can work with that data because it's in PDF format, right? So if we want to run WordCamp for Peru, and we got that we don't have the data so quickly. We have to, there's a bureaucracy way to get the data, right? So sometimes I feel that maybe as a researcher, we have to have a course in marketing to convince our government to have that data. So my question is, what about how we convince our governments, our political, that part? Thank you.
First thing I would say, it depends very much on your government. I don't know if you can convince the government of Brazil of doing this kind of thing. It'll be probably difficult. But I remember a few years ago, the Minister of Environment in Chile was an atmospheric chemist who had been trained in the US, and he created a wonderful network of observation and supported also modeling. So there are 3-4 models running in Chile. So it depends very much who is in the government and the interest of the people. And of course, some government will judge that they are more urgent questions than air pollution that they need to address. And this is why I called my presentation, do we need a worldwide system to really construct something that will be maybe sponsored by the World Health Organization or the World Meteorological Organization. Probably I prefer the World Health Organization because you have to convince meteorologists also that air quality is important, but you don't have to convince the health people that much because they know it. So, it's a matter of a daily action and trying to introduce this. You need good people in the countries that are respected. You need push from the population for these kind of things. I mean, look what happened in China. China, as I told you, was all about growth, development. And then suddenly the skies got gray forever. And the population said, we cannot work under those conditions. We're going to move away. And they had to do something. And now they're taking it very seriously and they're trying to solve the problem. So, and of course they had a very more acute problem than in Peru or in other places. But I think we need to, train people, educate people, and convince people. It's not easy.
Our future Ministry of Environment.
Yeah.
No, it's just an observation. Fatima and I, we are talking about the future project, and she thinks that we should study the emission of ships emission. So, yeah.
No, because here, Brazil has many problems. Brazil has not the same regulation as Europe concerning the emissions from ships. No, we have no regulation. Then we can use that very bad oil. And we have Santos, that's I think the third port in the world, and then we have in Vitória, we have many. But we never study this. I talked to Perola because she likes challenges.
Okay.
Well, there are a lot of ships cruising along the Atlantic coast of Brazil. They're going to Europe most of the time. And in Europe, they have to, very often they have two engines, and then they have a cleaner engine when they enter Europe, and then when they're outside, they use very cheap oil. And
it's the same that happens, because there, I know they have this regulation to use a cleaner oil there with less sulfur, things like that, but not here. And then it's very interesting because sometimes people say, oh, I'm going to do some sampling in Santos. Santos is the city near the coast because there should be cleaner. But when we look to the air quality, there is not only it's for particles, it's for ozone.
But I can give you the emissions of ships globally, so also along the coast here. And we could do a calculation to see what is the impact on the coast in particular.
It could be a good idea.
The wind is very much coming from the ocean very often.
Yes, because we have the circulation, the modeling of the sea breeze and all this, and then we have a very complex problem here concerning the ships. Someone?
You were sitting there.
Yes. So it's just that she doesn't have to walk, or I don't have to walk. So I guess this is the second part of my first question that was related to N2O. I guess it was forgotten, but I am curious about the initiative to model N2O, because in a country like Brazil, whose economy is vastly dependent on agriculture, it can be relevant.
Yeah. So sorry, I forgot about that. So what I can say is it's not a problem for air quality directly, but it's a problem for climate and for radiative forcing. And so N2O has been a bit the forgotten species. It has a lifetime of, 120 years in the atmosphere. And so it depends very much on the emission by soils, affected by fertilizers and so on. And also in the rivers and the ocean is also a little bit of an emitter. So doing a good study on the global budget of N2O would be something that is very important to do. And I haven't seen much on that for a while. There were papers 20, 30 years ago on N2O, but then everything is on CO2, and people forget that now there is a revival of methane. A lot of people now start to think about methane as a big question. So maybe you should introduce N2O, and then it'll become a big issue again.
Thank you.
Okay,
So I'm looking to the screen now.
Yes. Thank you, Dan. Thank you very much, Guy, for your very nice presentation. Thank you for being here.
Tchau, gente.
Tchau, tchau.